Thank you very much. Thank you for inviting me to give a talk to this kind of online conference. So I'm going to speak about a result. Probably some of you have already heard talks on this. It's a common work with Hrushovski and François Loeser. But I will try to focus not specifically on the result. I will mention it and say what it tells, but I will try to focus on the method and on the tools we develop for proving this result, because we think that these tools could be helpful for other purposes. So this work is based on the general philosophy, which perhaps goes back to Berkovich and Sorbonne's conjecture, or I don't know to which people attribute precisely this philosophy, but it tells this is this general principle. So principle, one parameter, families of complex objects often have a limit, kind of a limit, living in the t-adic, where t is the smaller parameter, in the t-adic analytic world, and especially in the Berkovich, in the sense of Berkovich, which is especially well suited for this kind of mathematics, in the sense of Berkovich. So there are several instances of this principle, and I'm going to speak about one which concerns integral. So let me first recall very quickly some facts about a theory of integration on Berkovich spaces, which was introduced by Chambert-Loir and myself. So first of all, integration of real forms. Real forms on Berkovich. What happens? Okay, on Berkovich spaces. So if you take X Berkovich spaces, analytic space, so always in the sense of Berkovich, over a ground field K, which can be an arbitrary non-Archimedean complete field, characteristic 0 or P, equal or unequal characteristic, algebraically closed or not, free values or not, we don't care. The theory works on any such field. So I take X analytic space. So with Antoine, we define first a notion of smooth functions. Of smooth function. This is a function, real valued on X, or an open subset of X if you prefer, real valued, which is locally of the form phi of log f1 log fn, where the f1, fn are invertible holomorphic functions. And phi is a smooth function. Phi is a C-infinity function. Perhaps not defined in the whole of R to the n, but defined in an open subset containing the image of a log absolute value of f1, log absolute value of fn. So this is with Antoine, this is what we call a smooth function, and we have a sheaf of PQ of forms, sheaf of forms. So it's a bigraded sheaf. So forms have a bidegree PQ, APQ, with two differential operators, with d prime and d double prime. Differential operators. And so A00 is just the set of smooth functions, the sheaf of smooth functions. And I will not define precisely what is APQ, but I will just define what D prime and D double prime do on very specific on specific expressions. So one has D, if I use a multi-index notation, D prime of phi of log absolute value of f, D prime log log fg. So I have apples and something like that. This is just the sum of D yes, there is also a wedge product in this on this complex of forms. And the same for D double prime, except that one replace this by D double prime for D double prime of all the expressions. So this is so I don't pretend to give a precise meaning, but this is we have these two differential operators and this complex of forms, and in fact locally every section of APQ is a sum of terms as above. So basically everything is built from smooth functions and by iterating derivations, D prime and D double prime, and by making the sum of such terms. Okay, and we have a theory of integration. So if L is equal to D mix, every compactly supported omega belonging to n of x can be integrated. So this is a well-defined real number. And so there are plenty of properties of this integration. There is also a boundary integral with Stokes formula and so on. I will not mention them now, but I would like perhaps to explain how this integral is computed in a quite simple case. But in fact, the general definition of this integral reduces to this simple case. So it's not only it's a simple example, but this is in fact the core of the construction of the integral. So construction of the integral, assume x is compact, affinoid, for instance, if you prefer. Compact but small. Usually it's by reasoning locally that one reduces to this case. So I don't have in mind x projective. I have in mind x a small closed disk, for instance, or something like that. Assume x is compact and omega is equal to phi of log f1 log fn and d prime log f1 wedge d prime log fn d double prime and the same. And where n equals d mix, I assume this, and I also assume that when I look at this map, log absolute value of f1, log absolute value of fn, and I apply it to x, the general theory says that this is a polyhedron with rational slopes and so on, but I assume that this is a convex cell, is a convex polyhedron, say P, and that the image of the boundary of X, there is a notion of boundary of a Berkovich space. It's not purely topological, it involves the sheaf of functions and so on, but there is a notion of boundary of a Berkovich space, and you assume that the image of the boundary is contained in the boundary of this polyhedron. So the image is a big cell in some sense, and the image of the boundary is contained in the boundary of the cell. And in fact, by arguing locally, you can always reduce to this situation, or at least omega will be a sum of terms like this, but integral is linear, of course, so it's sufficient to be able to integrate one such term. And then the integral of omega is just the integral on this polyhedron P of the function phi, now usual Lebesgue integral. But there is an integer, and I will explain how this integer is defined. So this is a degree, and what is this degree? So you have f1, fn. It's a map. These are invertible functions, so it's a map to the n-dimensional multiplicative group in the Berkovich setting. So the GM, I mean analytic, so in the sense of Berkovich. And in this, on this Berkovich space, you know that there is a canonical subset, which is called the skeleton, and which is homeomorphic to R to the n through the log of the coordinates. So there is Sn, which is homeomorphic to R to the n, and through log absolute value of T1, log absolute value of Tn. And now pick any point. So this map, let me call it F simply. Any point small x in this skeleton corresponding to a point of R to the n that belongs to P. So P is this polyhedron, which is the image of the space X under this under the norms of the log of the norms of the FIs. Then now I take any that belongs to the interior of the polyhedron. So I take a point of R to the n in the interior of this polyhedron. I take the corresponding point of the skeleton, and then F. This is one, it has to be proved, but then F is finite and flat above X, and D, the integer D I wrote before the integral, and D is its degree. So one has to prove that F is finite and flat above such a point. The degree does not depend on the point because P with the interior of P is connected. This is the interior of independent of X. Since the interior of a cell is connected. And so the integral we define with Chambert-Loir is the usual real integral on the polyhedron P, but there is an integer you have to put, you have to multiply it by an integer, which involves in some sense algebraic geometry or commutative algebra, because here there is a degree of homomorphism above a specific Berkovich point. The points of the skeletons are not classical rigid points. These are really purely Berkovich points. And so this definition mixes usual theory of integration of real forms on real spaces and algebraic geometry that plays a role through this degree. So this is the definition we use with Antoine. And now I will now state our result, our theorem with Hrushovski and Loeser. The statement of the theorem. So I will not state it in full generality because it is the formulation is quite complicated. I will roughly tell what it says and perhaps give an example in a simple case. So I take let M be the field of meromorphic functions around the origin of C, around the origin germ of meromorphic function, if you prefer, around the origin of C. X be, say, a projective, smooth, irreducible variety over M of dimension n. Then X gives rise to a family xt of complex algebraic varieties for t small enough and not 0, because it's on the field of meromorphic function. So for t belonging to d minus 0, d a small disk. Around 0. So I have this family. And now I can consider, now I can consider let omega t be a family, a reasonable family. I will not give the detail, but be a family of compactly supported n forms on the xt's. Okay, compactly supported is stupid. I told that the varieties is projective, so of n forms on the. I could give a version with affine variety with a non-necessarily projective varieties, but I want to make things simpler. So I take a family of n forms. Then, under certain assumptions, okay, well, it's too vague. Okay, I would say if omega t is a family, omega t is of a certain kind, we associate to it a form omega in the sense of Chambert-Loir and myself in ANN of xn. I will tell in 1 second what is xn. Xn. So what is xn? Xn is you take x, which is defined over M. Then you make a base change over the field of formal power series. So field of meromorphic functions is the field of convergent Lorentz series. Then you go to the field of formal. And now this is a non-Archimedean field. And then you take analytification in the sense of Berkovich. So if the omega t is a family of a certain kind, and I will give an example in 1 minute about what kind of, so what I mean by that, or at least show an example of a family of the good kind. So to such a family, one associates a form, and the limit for t going to 0 of the integral of omega t on, now let me write it like this. For every t, I can integrate on xt omega t, and then it tends to. So this is usual sense, and this is the sense of Chambert-Loir and myself. So this is an instance of the general phenomenon I mentioned at the beginning. We have a family of complex objects here, complex differential forms, and the integral of complex differential form on a complex algebraic variety. And it has a limit, and this limit is an integral of a Berkovich differential form on a Berkovich space. Okay, so what kind of example of good families omega t and of the form omega in the non-Archimedean world? So let f1 fn be rational function on x. So it is a projective variety, so it has no non-trivial invertible function, but I take a rational function, non-zero, Okay, and let phi be a compactly supported function, smooth function on R to the n. Then I can take omega t will be, so let me, 1 divided by log of absolute value of t to the n, 1 divided by 2p to the n, phi of log absolute value of 1 divided by log absolute value of t, log fn divided by log absolute value of t, and then we'll d log module fn, d log fn, wedge d argument f1, d argument fn. So the fn can vanish and have poles, but since phi is compactly supported, this is a well-defined form. There is no problem with that. And then, so this is a good family. It means that the limit of the corresponding complex integrals exists and can be interpreted as a form omega, as the integral of a form omega on Mixan. And let me describe what is the form omega. So I just have to, okay. So now on C double parenthesis T, I have a Berkovich absolute value. I mean a non-Archimedean absolute value. And of course, yeah, there is a choice. I can choose the absolute value of T, but I don't care. So there is, I will not be like Berkovich. So it's the non-Archimedean absolute value. And then the limit form is simply essentially the same, but you replace you replace essentially everything by the Berkovich counterpart. So it will be 1 divided by log absolute value of t Berkovich to the n. There is no 2 pi now. Phi of log absolute value of f1 Berkovich divided by log absolute value of t Berkovich. The same with fn Berkovich log absolute value of t Berkovich, and then d prime log f1 wedge d prime log fn wedge d argument, no, the d double prime, there is no d argument here, d double prime log f1 wedge d double prime log fn. So this means that the limit of these complex integrals will be the limit of this Berkovich differential form, computed as I explained before. So you reduce to small pieces on which the tropicalization is a nice cell, and so that the boundary, the image of the boundary is in the boundary of the cell, and then you will get a certain degree, you will get a degree given by commutative algebra, the computation of the degree of some of the finite flat map over given over a specific Berkovich point, and then you just compute the integral of phi on this polyhedron and multiply by this degree. So there is this non-Archimedean contour. This is the non-Archimedean integral, and it is equal to the limit of complex integrals. And I want to insist that the original definition of Chambert-Loir and myself worked on every field, and so the definition of our integral a priori had nothing to do with the limit of complex phenomena. It was not defined only on C double parenthesis T, it could work in characteristic P and so on. It was defined directly in the Berkovich world, but it turns out that when we are in t-adic Berkovich geometry, then there is a field of complex number, and then some forms arising from some Berkovich forms have an integral which can be interpreted as the limit of complex integrals. So,
Antoine?
Yes?
Do you have a version of this for PQ forms?
For PQ forms, we don't have integrals, of course, but in fact, yes, we have we have in fact a way to associate to if I take a reasonable family omega t of PQ forms, I will get a PQ form in the sense of Chambert-Loir and myself. But of course, there is no comparison with integration in this case because it doesn't mean anything. But part of our theorem is a way to associate to a certain family of complex form of arbitrary bi-degree PQ, a Berkovich form of the same bi-degree on the same essentially on the same variety on the analytification of X. And so now, I will not have time enough to describe the proof. And in fact, there are a lot of computations, so it's not so easy to. Even with 2 or 3 hours, it would not be so easy to explain the proof in an understandable way. But I will try to, in order to do this, we introduced an object, and I think that this object could be useful for other, for studying other phenomena analogous to that one. I mean, other t-adic non-Archimedean limits of usual complex phenomena. So I will now try to describe and insist on our construction. So our idea is to, instead of so here I had the field of meromorphic function and C double parenthesis T and so on, and so I had the family of complex objects on one hand and the non-Archimedean object on the other hand. The idea is to be the field, a huge field, which in some sense will encode in the same field both phenomena, the Archimedean limit phenomena and the non-Archimedean phenomena will be encoded in the same field. Archimedean limit phenomena will be encoded by kind of a non-standard analysis on this field. It will be analysis, but with infinitesimal or infinitely large elements. And on this field, there will be also a usual Berkovich absolute value. And so on the same field, we will be able to encode limits of usual Archimedean phenomena and non-Archimedean phenomena. And so it will allow it will be very convenient for direct comparison and even for writing the statements. For example, the statement that Lorenzo asked me about 2 minutes ago is really, I hope I will have time to explain it. It is really convenient to state it not with limit of family of forms, but not with family of forms, but with non-standard form on a given field. So what is our construction based on? So we fix U an ultrafilter. So of subsets of all the complex of all the set of complex numbers. So arbitrary ultrafilter, and I just want that that every if it is non-principal. I don't want this ultrafilter to be the set of subsets containing the origin, because then it would be stupid. It is non-principal, and I claim that 0 is in the closure, which means in fact that for every open subset U in C, if 0 belongs to U, then the complement, when you punctured this neighborhood, belongs to the ultrafilter. So I want to be able to take, in some sense, limits of things going to 0, but working with ultrafilter is a way to avoid replace at every time a sequence by a converging subsequence or things like that. Essentially, the axiom of choice does the job for you, and everything converges. This is the idea. And then, if I so by notation, if I consider a family something like that, it will always be understood. It will be understood. So if I take something with a t as a parameter, t as an index, it will be understood. That t belongs to some subset U of C belonging to U, to the ultrafilter. And this subset U is not important. I mean, if I need, I can shrink it, provided I'm still in the ultrafilter. So I will consider these generalized sequences if you want. And now with this, I consider, so and I will say that, that some property of the xt's holds along U, along the ultrafilter, if the set of t such that the property holds belongs to the ultrafilter. When you have a subset of C, there is because it's an ultrafilter, either this subset belongs to the ultrafilter, either its complement. And so if I have a given property of the element xt, whatever kind of mathematical objects there are, if the set of t for which this property is satisfied, I say that it is satisfied along U. And if a property is not satisfied along U, its negation, it's satisfied along U, because if a set is not in the ultrafilter, its complement is in the ultrafilter. Okay, and so now with this, I can build a huge field. So what will be this huge field? I will denote it by a star. It's non-standard complex number. It's just the set of all sequences like this with zt in C. Divided by the relation that zt is equivalent to z prime t if zt is equal to z prime t along U. So eventually along my ultrafilter. And so star C is an algebraically closed field. So the addition, term-wise addition and the multiplication, and star C with the structure of a ring and actually of a field, and this is an algebraically closed field. Which it is containing a real closed field, which is real closed. Oh. And so the situation looks very similar than it is with R and C, but these are non-standard models of R and C, which means that also there is an order relation on R. So you can also define the modulus of an element of C just by taking the square root of a square plus b square and so on and so on. But this is non-standard in the sense that infinitesimal elements or infinitely large elements are allowed. So for instance, if I take the family zt with zt equal t for every t in C, then I get an element of C star, of star C, which I still denote t, denoted by t, which is its absolute value is infinitesimal. So this t should be thought of as a complex number going to 0 if you want. But formally, this is an element of a non-standard model of C with an absolute value, and its absolute value is an element of a non-standard model of R, and it is infinitesimal, smaller than every positive, but smaller than every rational number, that every usual real number. And so over the field of R or C, one can evaluate usual smooth functions. By usual, I mean smooth function, say, defined on the field of usual real numbers simply by evaluation.
Antoine, can we
Yes.
interrupt you? There's a question in the chat. What is the codomain of the absolute value of this new complex number field?
This is the set of positive non-standard. So the absolute value of this field is just the set of positive non-standard real numbers. Because, okay, so this is another. So everything is very similar to what happens on C or on R, except on C and R, except that you allow infinitesimal and arbitrary large or very, very large elements. So T is a typical example of an infinitesimal element, but you can of course have plenty of others. And so you can evaluate smooth function by evaluating evaluation term-wise. Evaluation term-wise. On a sequence. ZT, so you take a smooth function, imagine, say, for instance, if your ZT are real numbers, you take a smooth function, you take your sequence of parameterized by T of real numbers, and you evaluate, and you get a new sequence, which gives you a new element of your field. And so it's possible to define, one can define a sheaf of a differential form or of PQ forms also, of PQ forms on a variety X over star C or over star R. So I will not be, I will just say a few words without without writing them. So C or X over star R. So when I say that one can define a sheaf on such a variety, I am speaking in fact about its set of points or about its set of non-standard complex points or non-standard real points. And when I'm speaking about a sheaf, one has to be a little bit careful because star R is an ordered field. So certainly it has a topology given by the order. And since star C is just a two-dimensional vector space on it, it also inherits a topology. But this topology is rather pathological because there are a lot of awful Dedekind cuts in the field star R. So when you want to deal with sheaves, you have only to allow reasonable open covers, and this is done through the language of Grothendieck topology. So there is a notion of admissible or whatever cover, so it's called the semi-algebraic topology. So it's basically this is the order topology, but without allowing pathological coverings. Typically, our full Dedekind cuts gives you a cover of star R with two not really interval or the interval with endpoints that don't live in star R. This you don't want as a cover, but interval with actual overlaps you accept as covers. And so you have, and there is also a theory of integration. One can also integrate. One can integrate compactly supported forms. Just point-wise, just term-wise on the sequence. You compute the integral of you have a sequence of algebraic of a variety over this field. You can see it by looking at the coefficient of the equation of the variety as a family of varieties parameterized by T. Idem for the same for the forms, and then you can integrate for every T, and then you get a family of real numbers, and this family of real numbers gives you an element of your field, so star R or star C, depending whether your form is real valued or complex valued. So this is quite easy in some sense. This is perhaps you are not that much used with ultrafilters and so on, but it's not very difficult. Now the point is that this is not exactly the field we want to work with, because these fields are too large for us, and we will need to, because we are only interested in t-adic phenomena, so we don't want we will need to consider only a specific element of star R and star C. So now let us say that an element of star C, say, is T-bounded Remind that t is very small. So if an element z, if z is smaller than 1 over absolute value of t to the n for some n in n, and t negligible if for all n. And then what I really am interested in is the following. Now let C without a star, but also without not bolded, just C. Let C be the set of T bounded modulo T infinitesimals. And let R the same in R. So it was T bounded in inside star C, and this is the same, but inside star R. And then these are the objects we want really to work with. So now C is algebraically closed field. C is algebraically closed. R is real closed, and C is equal to R of square root of -1. So the situation is quite similar, except that what makes things technically more complicated is that our former huge fields were directly defined as ultra products using ultrafilters. So basically everything you can define on R, you can define on star R and star C just by defining it term-wise. Now, this is more complicated because there is you only consider T-bounded element, and there is a quotient by the T infinitesimals. But okay. Nevertheless, so what is this field? What can one do over such a field? Let me explain. So one can still define smooth functions on C, or over C or over R, but one has to be a little bit careful because one over C or R, but one has to define them. Okay, the idea is you take an element of C, you lift it on star C, and then you apply the smooth function, but then you should be sure that when you will reduce modulo the T infinitesimal, it does not depend on the lifting. And so you have to be a little bit careful because you will not be able to evaluate all smooth real functions. You have to ensure some boundedness condition to be able to do this. But it's a little bit, but one has to work. One has to work. Not every smooth real function gives rise to a smooth function over these fields because of the quotient. One has to ensure that one can quotient and without ambiguity. But for most of them, it will be okay, but one has to be careful. And then one can define sheaves of differential forms. And integration. But again, everything is by lifting, computing on star R or star C, and reducing modulo T infinitesimal. And reducing modulo T infinitesimal elements. And of course, one has then to ensure that it does not depend on the lifting. And so this is here one has to work especially for the definition of smooth function already, and for the integration. This is part of the paper, consists in showing that the theory of integration of smooth forms, of compactly supported smooth forms, is well defined over the field C or over the field R. And there is some, so at some point it uses some minimal geometry because one wants to prove that basically that some definable, some semi-algebraic subsets have t-negligible volume or things like of r to the n, of star r to the n have t-negligible volume or something like that, and you do it using induction on n and cell decomposition and things like that. So there is a O-minimal geometry involved. But now one of these functions, so log of absolute value of z, is a smooth function on C. And in fact, now if I divide, because every element of C comes from a t-bounded element, if I divide log of absolute value of z by log of absolute value of t, so t was a t-bounded element of star C, so it gives rise to an element of C, which I still denote by t, then is bounded in the sense that it is belongs to minus n for some integer n, for some usual integer n. It is bounded. And then when you have an element of a big real closed field or a big model of complex number that is bounded, it has a standard part. It has a unique writing as the standard part, standard of log z divided by log t, plus what? Plus an infinitesimal, plus epsilon, which is infinitesimal, in the sense that 1 over n smaller than minus smaller than for, or if it, okay, let me just, I will use absolute value if these are not real but complex. Let me just, epsilon is smaller than 1 over n for every n in n. So when you divide log absolute value of z by log absolute value of t, you get something which is not a real number, but it's a real number plus something infinitesimal. You forget it's, the decomposition is unique. You forget the infinitesimal part, and then you get a real number. In fact, if I look at this, log z divided by log t, and then I take this standard part, then this is a non-Archimedean valuation. Which is a t-adic, you know, it's just the exponent of t in some sense in the absolute value of z, except that one has to keep only the standard part and to remove the infinitesimal part. So it's a non-Archimedean valuation, and C, in fact, is C is complete, and even spherically complete. For this valuation. And the value group is the whole R. The value group is R. So now C is interesting because it is a field in which non-standard analysis is encoded, because there is this infinitesimal element t and the powers of t, and so one can encode in C by non-standard analysis. One can encode in C the usual limits of standard phenomena in analysis, but C is also a t-adic complete field, far bigger than C double parenthesis t. But nevertheless, this is a Berkovich field of characteristic 0. The value group is R. It is spherically complete. You can do Berkovich geometry on it. And then now I can just explain quickly what our theorem says. Then if X is a projective okay, even don't need projective. If X, if X is an algebraic variety over C, then we define, say, a vector space or a complex, a big graded In fact, it's a sheaf also, but because we can restrict to Zariski open subset. But let me just speak about global section. A big graded complex of vector spaces, say BPQ of X, consisting of not all, but of some differential forms. Of some differential forms on this, and there's and a morphism and a map. Morphism, say a morphism from BPQ of X to APQ in the sense of Chambert-Loir and myself of X analytic, commuting so to addition, differential operators, wedge products. So a nice morphism. And so this answers the question by Lorenzo at the beginning of the talk. And if P equals Q equals N, and if omega belongs to BPQ, so let me call it omega dot omega Berkovich, maps to omega Berkovich. If omega belongs to BPQ of X and is, say, compactly supported, then omega B is compactly supported. The integral on X of C of omega is bounded, so it has a standard part and an infinitesimal part, and the standard part of this integral is equal to the integral of this omega Berkovich. So I think you told me 55 minutes, so probably it's a good idea to stop here, or perhaps say a few words, but I don't write anything more. So this is the way we state the theorem, and especially with this morphism of, so I don't know which name to give to these structures because there are a lot of things involved, but this morphism, there is a natural way to associate to certain, not all differential forms, of course, they have to have a certain form, but we can associate to all these non-standard differential form on X of C, which can be sort of a kind of family of standard differential forms involving elements going to 0 or to infinity. I can associate to each form like this, a form on the Berkovich space in a way compatible to addition, to differential operators, to wedge product, and perhaps more important, this is compatible with integration, in the sense that when we integrate such a non-standard form, you get a non-standard number, but bounded, which means that it's close to a usual real number. You forget the infinitesimal part, you just take the real number, and this real number can be also computed as a Berkovich integral. Okay, so I think it's a good idea to stop here and perhaps to answer questions if there are some.